Condition-based maintenance, or CBM, is an ever-growing and increasingly proven methodology of repair and upkeep over a wide variety of military and civilian applications. The concept of CBM, in which the measurable condition of a component dictates the appropriate maintenance action to be performed, has not only shown itself to be effective, but also cost-saving. The objectives of CBM seek to reduce the logistical footprint of scheduled maintenance by performing repairs only upon evidence of need, thereby significantly increasing operational capability while at the same time reducing costs. In 1984, the South Carolina Army National Guard at the McEntire Joint National Guard Base in Columbia, South Carolina, began developing embedded electronic devices to assist with helicopter rotating component condition determination. As interest in this type maintenance grew, the Army National Guard sought a partnership which could assist with the refinement and qualification of this new technology. Conveniently located 40 minutes to the west in downtown Columbia is the University of South Carolina, the largest university in the state, with a strong reputation in engineering. With access to top-of-the-line research equipment and fabrication technologies, the university's College of Engineering and Computing was more than capable of meeting the needs of its new partnership. Currently, the Department of Mechanical Engineering hosts a fully matured research program dedicated to the advancement of condition-based maintenance. The primary objective of the research efforts at the University of South Carolina is to develop and advance the application of cutting-edge diagnosis and prognosis algorithms, specializing in the study of rotating helicopter components. To achieve this objective, more than 100 million records have been collected from a combined source of health unit monitoring systems data and maintenance logs. The collection of this historical data serves to create a baseline by which to measure and compare component performance, usage, wear, and failure. Enhancing this considerable undertaking is the implementation of customized test stands, which allow seated fault components to be carefully examined during failure under normal operating conditions. Forming the backbone of the historical data collection is the Army Maintenance Management System for Aviation, known as TAMS-A. These records traditionally consist of handwritten logbooks which list every observation and action performed by maintenance crew personnel to a given aircraft. As technology has progressed, the Army has moved much of these logbooks to a computerized form for easy storage and retrieval, allowing the entire history of a particular aircraft to be accessed within seconds. Since 1998, the CBM team at the University of South Carolina has been collecting these types of maintenance records from various aircraft all over the world, creating a thorough baseline of historical data from which parameters such as logistical overhead and unit readiness can be evaluated. Additionally, the CBM team currently has access to a wealth of data collected by Health and Usage Monitoring Systems, or HUMS. The implementation of these systems requires the installation of several sensors at various points in the aircraft and typically focuses on vibration levels of specific components during flight. The output of these sensors are collected and monitored by a central signal processing unit, where they are analyzed to determine a condition indicator for that region. Throughout the flight, these condition indicators are calculated and stored, creating a vehicle health profile that can be downloaded to a computer and examined to determine what maintenance actions are required. Guiding the research activities of the University of South Carolina, the initial phase of data analysis consists primarily of hotspot identification. The goals of these investigations are to identify which components of the aircraft show a strong relationship between TAMS-A maintenance actions and HUMS condition indicator anomalies. From the collected set of condition indicators, statistical analyses are performed to identify the central tendencies of each indicator for each aircraft type. Events that show a large deviation from the mean are identified as anomalies and are extracted for further analysis. Based upon the aircraft tail number and incident date, corresponding TAMS-A records are extracted to find potential causes or effects of the event. When a potential match between the two data sets is found, it is used to direct the research efforts into examining components that will most likely produce results. The CBM team at the University of South Carolina, with support from the South Carolina Army National Guard, has developed versatile generic test stand platforms designed to test a wide variety of rotating helicopter components. The adaptable framework of this design allows for the testing of individual helicopter components or entire component systems. The current configuration of this stand emulates a full-scale AH-64 Apache Longbow tail rotor drivetrain and is capable of simulating normal operating conditions of an Apache in flight. It includes 4 drive shafts, the forward and aft hanger bearings, the intermediate and tail rotor gearboxes, and the tail rotor swash plate. These components are assembled and aligned with assistance from Army National Guard personnel to create a realistic environment to examine fault propagation in the helicopter components. The test stand is driven by a custom-built 800 horsepower motor which is capable of running at 120% of the normal operating conditions of the Apache. On the tail end is an absorption motor capable of controlling the torque on the drivetrain by providing the same resistive load that an actual tail rotor would encounter in flight. The test stand is equipped with an industry-standard HUMS kit capable of producing the same summary data and condition indicators defined for an actual Apache helicopter. Additionally, the CBM team at the University of South Carolina has installed a wide variety of additional sensors which record and monitor component conditions at a higher rate and precision than a standard HUMS device. The data acquisition system also serves as the drivetrain controller, able to operate the test stand for predefined time intervals or, in the case of a component failure, automatically shut down the system. This same type of smart monitoring is applied while collecting data. When a failure or unexpected event occurs, the system intelligently monitors and records the event with a higher degree of precision. The CBM team at the University of South Carolina has already begun baseline signature testing on its Apache tail rotor drivetrain test stand. These activities are now expanding to include seated fault components such as misaligned and unbalanced drive shafts, as well as faulted and used hanger bearings. Additionally, the CBM team has recently completed the construction of an Apache main rotor swash plate test stand capable of speed and loading conditions encountered by an Apache in flight. Also under development is the construction of a UH-60 Blackhawk tail rotor drivetrain configuration. The current system framework is easily adapted to interface with Blackhawk's design and will require relatively few modifications to the existing test stand platform. Utilizing all these tools, the University of South Carolina seeks to advance the field of CBM by targeting specific CBM objectives. First is the linking and integration of millions of collected TAMS-A and HUMS data records, and to quantify the usefulness of each field in order to increase the efficiency of the ongoing research. This integration is achieved by a second objective, reaching an understanding of the underlying physics and root causes of component and system faults. These two goals are a constantly refining process. Hotspot identification leads to experimental design test plans, the results of which can lead to an enhanced ability to identify more links between the data sets. The ultimate result of these first two objectives is a fully integrated knowledge of the interactions of vehicle condition indicators and maintenance history. As this integration becomes fully realized, new possibilities emerge which will allow the University of South Carolina CBM team to achieve the ultimate project objectives: diagnosis and prognosis. The first of these goals, diagnosis, will seek to define algorithms that utilize TAMS-A and HUMS data in the early detection of faults. Advanced knowledge of component failure serves one of CBM's core purposes: to reduce costs associated with unscheduled and unexpected maintenance. The second goal, prognosis, will identify algorithms that can accurately predict the remaining life of components and component systems. In doing so, repairs and replacements will only be done to parts that need it, thus reducing the overhead and costs of unnecessary maintenance. Integration, understanding, diagnosis, prognosis. By accomplishing these four objectives, the University of South Carolina's Department of Mechanical Engineering is and will be an invaluable contributor to the efforts of condition-based maintenance. With a versatile and adaptable test platform for research and a wealth of historical data, this project will inevitably see results for a wide variety of aircraft and components. Condition-based maintenance has proven itself to be the way of the future, and the University of South Carolina is proud to be a part of it.